All right, so like I said, today's our last review day, our last day in chapter 15. So let's start today with a review question from yesterday. So we are told that the concentration of ammonia in household cleaner ranges from between 50 and 100 grams per liter, which on the molarity scale would be somewhere between 3 and 6. What we want to know is what is the pH of 3 molar ammonia solution? And the Kb value for ammonia is 1.76 times 10 to the negative fifth. So just as a reminder from yesterday, what you're going to need to do here is set up an equilibrium expression and using an ice table, turn that starting concentration of ammonia, 3 molar, and that Kb value, figure out the concentration of hydroxide, turn that concentration of hydroxide into a pH value. So I'll give you a couple minutes to kind of work that out, and then we'll come back and look at our results. So at the heart of all of these kinds of questions is the fact that we're going to have to draw ice tables for all of them. And so that's one of the reasons why we introduced that concept in the last chapter. We're continuing to use them over and over and over and over. And so if your first instinct out of sheer reflex for this problem wasn't to draw an ice table, that's something that you're going to have to kind of teach yourself, train yourself to do, is that you can always write an ice table and realize I'm not going to need this. But if we're talking about equilibrium calculations of some kind, ice tables are at the heart of well over 80% of them. So the reaction question was this one that I gave you here in purple. Since water is a liquid, we are not going to be concerned with its concentration. So what it comes down to here is this. We've got X for our concentrations at equilibrium of the ammonium ion and the hydroxide ion. And we've got 3 minus X for the concentration of the ammonia. So what do we do from here? Well, we can set up our equilibrium expression, and this is going to give us X squared, X times X, over 3 minus X equaling Kb 1.76 times 10 to the negative fifth. Now, you can go through this and solve the quadratic. However, this is also a good place where we can always take a peek at the 5% rule and see if that gives us a shortcut so that we don't have to solve the quadratic. And remember, the 5% approximation if 5% of the starting concentration is still bigger than K, we can ignore the minus X term. So 5% of 3.0 molar is 0.15. 0.15, 1.5 times 10 to the negative first is 4 orders of magnitude greater than our K value. So yeah, we can skip that. That makes this a little bit easier, because what this means is that we can approximate that this expression is equal to x squared over 3.0. And that's a lot easier to solve. I don't need a quadratic to solve that. I just multiply 3 times 1.76 times 10 to the negative fifth, which gives me 5.28 times 10 to the negative fifth is equal to x squared. And so x must be the square root of that. To two significant figures, because we only had 2 here. 7.3 times 10 to the negative third. Since X is the concentration of the hydroxide, I can take that value and immediately find the POH. POH is equal to negative log of 7.3 times 10 to the negative third. Which would be 2.14. pH would be 14 minus 2.14. So 11.86. So this is what I was getting after in this particular problem here in the exam as well, was since we had such a large value of K and large concentrations of our starting products, it's kind of like the opposite thing. Instead of a small value of K and large concentrations of reactants, big value of K, large concentration of products, it's going to be a very product-driven, product-favored reaction. The minus X's, or in that case, the minus 2X's, were going to be largely negligible. So we could have ignored them. X ended up being like 0.05 or something like that. So barely changed the concentration of the chlorine in the problem. That's one of the reasons why I made that change, because if you tried to solve it the other way, you couldn't use a 5% approximation. You end up getting a x to the fifth factor. Super duper messy. Any questions with this review example from yesterday. So we talked yesterday about the relationships between pH, pOH, and 14, which is pKw. And we also looked at the relationship between the hydroxide concentration and the hydronium concentration and the autoionization constant for water, Kw, 1 times 10 to the negative 14th. And we talked briefly, we didn't get too deep into the math here, and I'm not going to elaborate deep on the math either, but we were able to determine mathematically why that relationship on the top exists and how it came from the relationship on the bottom. Well, there's another such manipulation that we can do using our Ka and our Kb values. We know that Ka multiplied by Kb will give us our Kw value. So this whole idea of conjugate theory quantifies itself with these constants. If I look at the Ka value for nitrous acid, what I will find is that the Kb for the nitrite ion is directly related to this concept. And that's why we could say that the stronger the acid is, the weaker its conjugate is going to be, because there's a finite limit to their product, 1 times 10 to the negative 14th. And so the bigger the value of the Ka is, the smaller the value of the Kb will have to be as a result. So if I have a really strong acid, its conjugate has to be really, really weak. Otherwise, this relationship does not exist. It does not work. And if I do the same kind of logarithmic manipulation that we saw on each side, what we get is a similar kind of relationship between the pKa and the pKb for a conjugate pair. pKa plus pKb is going to be equal to 14 as well. So a lot of times we will see the acidity of an acid, its strength, listed off as a pKa value instead of a Ka value. And one of the reasons for it is simplicity. Instead of a really, really, really small number, I can give a pKa value that is a lot more manageable. Instead of something times 10 to the negative 11th, I can say, okay, well, the pKa is 10.85. So what this tells us is that there is a relationship between the Ka and the Kb for a conjugate pair. And all I need to know is that they're both related to this Kw, just like pH and pOH were, just like hydronium and hydroxide were. So what this allows us to do is we are able to calculate Kb values for conjugate bases and calculate Ka values for conjugate acids. All we need to know is what is the K value for the other half of that pair. And then all I need to do is just divide that appropriately. So Ka times Kb is equal to Kw, which is 1 times 10 to the negative 14th. And so rearranging for either of these, I can figure out that Kb is equal to Kw divided by Ka, and that Ka is equal to Kw divided by Kb. Now it just becomes a matter of finding the conjugates here. So if we're looking at iodate ion would be the conjugate base, add a hydrogen ion, to iodic acid, HiO3. I just need to find the Ka value of iodic acid, and I'd be able to figure out the Kb value of its conjugate. To do that, I need to go to my appendix tables. Iodic acid has a Ka value of 1.7 times 10 to the negative first. Which means that the Kb value would be 1 times 10 to the negative 14th over 1.7 times 10 to the negative first. Which would be 5.9 times 10 to the negative 14th. So by most reasonable logic, even though we wouldn't classify iodic acid as a strong acid per se, its Ka value is not greater than 1. It's still reactant favored. It's a pretty robust weak acid. And as a consequence, its conjugate pair, its conjugate base, the iodate ion, is a lousy base. That base is almost as basic as water. Now for the hydroquinoline, we're talking about this acid here. So if it were to act as an acid, it would ditch that H plus and leave behind C9H7N. That's quinoline. So what we need is the Kb for quinoline. Again, we got to go to our appendix tables. And we find that the Kb for quinoline is 6.3 times 10 to the negative 10th. This is not altogether that surprising. Most of your organic nitrogen-based bases, you can go through this list, can range in quite wide varieties of basicity. Some in the higher ends of the scale, some on the lower ends. This one happens to be a pretty weak base. which means that this conjugate, after we divide it into Kw, (1.6 times 10 to the negative fifth), this conjugate is actually right on the scale of acetic acid in terms of its acidity. Now, the question you might be asking yourself with this is, okay, I get that there is acidity and basicity in these conjugates, but where would we actually see these kinds of conjugate values? Why would we even care about this kind of stuff in the first place? What is the application? Well, the application, we'll come to polyprotics here in a second. The application here is in salts. In salts, what we have are those circumstances where we might see the conjugate acids and bases of other substances in play. You think of kind of the most typical salt that there is, sodium chloride. Have we actually taken a moment to think about where sodium chloride actually comes from? We know it's everywhere. But how would we make it from nothing? Well, one of the ways that we could do it is we could take sodium metal and chlorine gas, put them together in a chamber, get them to form through this really violent reaction. The other common way would be through a neutralization reaction. We take sodium hydroxide and hydrochloric acid, put them together, and what we get is water and sodium chloride, salt water. And so much is the same for a lot of the other salt compounds that we would expect to see. Salts are the natural product of an acid-base neutralization. The question just is, what is the acid and what is the base that is ultimately coming together? And this is where this conjugate idea is going to take root, because we'll be able to see, okay, that salt was made by this weak acid and this strong base, and here's what we would predict its acid-base qualities to be. And using that conjugate character, here's what we expect the pH of that salt to be, at least theoretically. So that's where those two ideas kind of come together, is not so much, okay, here's this acid, figure out its pH. Here's this base, figure out its pH. Figure out the pH when they come together. But more along the lines of, here's this salt. I know it has activity toward acidity. What is the pH? What will that acidity actually look like when I dissolve that stuff in water? And so that's kind of the direction that we're going to be going for the majority of today. Want to clean up one little piece here regarding polyprotic acids, just because it will come up. It does come up. And if you look at these appendix tables, you will notice that when we have an acid that has multiple acidic hydrogens on it, there is a couple of key trends that we can see. First of all, we can see that each one of those acidic hydrogens comes off in succession. They don't come off all at once. So that idea that we gave you in Gen Chem 1, Chem 105, where we said, okay, yeah, sulfuric acid, when it dissolves in water, boom, you've got two hydrogens. You've got a sulfate ion. Reality is it's not quite that way. We will definitely get one hydrogen, Ka value for that first hydrogen coming off, very, very, very large. Ka for that second hydrogen coming off, not bad, 0.01, but not a complete conversion. We're going to have an equilibrium between the hydrogen sulfate ion and the hydrogen ion and the sulfate ion. And so when we look at polyprotic acids, that's what we have to recognize. Those acid protons are going to be released successively, one after the other. And each successive deprotonation is going to be harder to do than the first one. And that difficulty is going to show up in the value of the Kas. The Ka for the second deprotonation is always going to be less than that for the first deprotonation. And if there's a third deprotonation, that one will be even harder still. There aren't a whole lot of acids that deprotonate 3 times, to be honest. There are some. But by that point, unless you're dealing with a particularly strong acid, those successive deprotonations become harder and harder and harder to do. And we start to see, even in the second deprotonation, we start to see a tendency toward Ka values that are starting to tip onto the really weak side. We start to get below that 10 to the -7th mark on our K values. We start to see a tendency toward that conjugate base actually being better at being a base than that substance is as an acid. And if you have the case here where you've got something like HSO3, which is actually amphoteric and can go either direction depending upon its environment, that can play a role into terms of how it actually performs as either being acidic or basic. Carbonic acid is a great example of this. If you look at the Ka values for carbonic acid, what you will see is that you've got a substance here in the hydrogen carbonate ion that really doesn't like being an acid. And its conjugate character off of that deprotonation, it's actually better as a conjugate base than it is as an acid. And so what do we notice about bicarbonate compounds? They tend to be basic instead of acidic. Even though carbonic acid, we think of it as having 2 acidic protons, it's not going to behave that way unless we introduce it to a substance that is even more basic than it is. And so the tables in your book give us a little bit of insight into that as well. The appendix tables do that also. One thing that you will not get from me, some professors and some examples in the textbook will go through this really grand, large equilibrium problem where you have to figure out the total pH of an acid like phosphoric acid or carbonic acid or something like that. And it's a really involved problem because you've got to layer in all of the equilibria with each other. We're not going to get that here. And the main reason for that is because I don't see a whole lot of value in spending an hour to do a problem that has very limited applicability. So you should not encounter any problems like that in the homework. If you do, let me know. I'll remove them from the pool because they shouldn't be there. So let's come back to this idea of salts. And what we want to look at in particular is we want to make sure that we have a really good handle on where the acidic and basic properties of a salt are going to come from. And so when it comes to the ions themselves, what we'll see is that the anions are going to drive the basic character because the anions are the conjugate bases of whatever acid was used to make the salt. So if a salt is going to be basic, it's because of the action of the anions toward water. And so anions can come in one of two forms. They can either be inert, where the acidity of the acid that they came from is so strong that their Kd values are practically zero. So we see this for things like the chloride ion, the nitrate ion. Or they can have basic tendencies where the acid that they came from was a weak acid and the basicity that they have is really inversely related to just how weak that acid was. So the weaker that acid was, the stronger its basic character is going to be. Good examples of this are things like acetate, where we know that acetic acid is a weak acid. So the acetate ion itself is going to have some basic characteristics. The fluoride ion. We know that hydrofluoric acid is a weak acid, so the fluoride ion is going to have basic character. On the flip side, the cations themselves, they are going to have the acidic characteristics. And they fall into two categories as well. Those cations can either be inert, meaning that they come from strong bases, in particular strong hydroxide bases, your lithium hydroxides, your sodium hydroxides, your potassium hydroxides. Those ions are going to tend to have inert character, not going to impact water at all. Those that are acidic are going to be acidic for one of two reasons. Either as conjugate acids of those nitrogenous bases, we're going to see that basic character of ammonia or pyridine or quinoline or whatever that organic nitrogen compound is. Its basicity is going to have a direct impact on the acidity of its conjugate. The more basic it is, the less acidic the conjugate's going to be. But we also have here metal ions. So for those hydroxide bases that do not classify as strong bases, their ions, their metal ions, are actually going to be acidic in nature. Now, we're not going to get too deep into how they become acidic. Just know that it has something to do with their formation of complexes with water and how those water molecules can ditch a hydrogen to add some acidity from that complex. Again, we won't get too deep into it. That's an organic that's an inorganic kind of concept for a junior level course. We're not going to touch it here, but that's how we get acidity from those. Because you might be sitting there wondering to yourself, okay, well, how do I get hydrogen ions from iron 2+? It doesn't make sense. It comes down to their coordinate chemistry, comes down to their formation of those water complexes that stabilize those ions in water, and how those water complexes can have some acidic tendencies based on their environment. Now, where it can get tricky for us is when we have those amphiprotic ions. So these are the ones that we kind of started looking at the beginning of this chapter. The ones that are kind of in the middle of that polyprotic scheme, where I add a hydrogen and it becomes sulfurous acid. I take away a hydrogen, it becomes the sulfide ion. I add a hydrogen, it becomes carbonic acid. I take one away, it becomes carbonate. I add a hydrogen, it becomes dihydrogen phosphate. I take one away, it becomes the phosphate ion. That amphoterism, that amphiprotic nature, is going to mean that that substance is never going to be neutral toward water, because we can see it constantly either adding hydrogens or taking hydrogens away. So it's always going to act as an acid or a base. Which one it acts as depends upon the relative values of the Ka and the Kb for that particular ion. So what you have to look at is you have to look at their conjugate values. And if, when we explore those conjugate values, the Ka for that ion is better than the Kb, then we know it'll act as an acid. But if Kb is better than Ka, we will know it acts as a base. So the example that we give for this one is if we look at something like the hydrogen carbonate ion, which we can look and see that its Ka value is 4.7 times 10 to the negative 11th. Which says a lot about the acidity of the bicarbonate ion. It's not very acidic. But is it acidic enough? Well, for Kb, I need to look at the calculation that we did at the beginning of this, comparing the Ka for carbonic acid to find the Kb for the bicarbonate. And this was 4.4 times 10 to the negative 7th. we get 2.3 times 10 to the negative eighth. So in this case, the Kb for the bicarbonate ion is better than the Ka. We would anticipate that if all things are held equivalent, the bicarbonate ion is going to act like a base. It's going to be a basic ion if left to its own devices. And the most common example of that is baking soda. Baking soda is sodium bicarbonate. And what are the things that we know about baking soda? It's a relatively cheap antacid. It's a good stabilizer. Has a relatively basic pH. This is why. We could do similar kinds of quantitative studies for the other ions on this list and kind of uncover their natural tendency if we were to put them into water with other neutral ions. So when we are presented with a salt and we're trying to figure out qualitatively if it is acidic or basic or neutral, this is what we kind of have to do. There are 4 possible scenarios. The first is that I look at the cation, I look at the anion, they're both inert. Well, what does that mean? Well, it means that the salt's inert as well. We would anticipate its pH to be really close to 7. Second scenario, we have a cation that's inert, but an anion that is not. What does that mean? Well, since the anion is basic, that means that the salt should be basic as well. We could have a situation where we have a cation that is active, but an anion that is inert. Well, since cations are acidic, that means the salt would be acidic as well. We could also have the chaos situation, where the cation and the anion are both reactive to water. And in that case, you have to do a comparison. Which ion is more reactive? Which one has the stronger value of K? That's going to be the one that dictates acidity or basicity. And so your book summarizes this, table 1510. And I think one of the nice things about table 1510 here is conceptually, everything I just told you is accurate. If a salt is basic, it's because of the anion. If a salt is acidic, it's because of the cation. If a salt is neutral, it's because the 2 species have neutralized each other, basically, or they were never reactive in the first place. But there's an easier way to do this qualitatively. And the way to do it qualitatively is to look at the character itself. So when I evaluate a cation, what I need to do is I need to look at where did it come from? What is the formula of the base that made it? And is that base strong or weak? And when I look at an anion, I need to look at where did it come from? What is the acid that made it? And is that acid strong or weak? And what I can do is I can compare that base and that acid to each other. And the one that is stronger will tell me the strength of the salt. And that's what this table tells us. If I have a strong acid and a strong base coming together to make a salt, the result will be a neutral salt. If I have a strong acid and a weak base coming together to make a salt, the resulting salt will be acidic. If I have a weak acid and a strong base coming together to make a salt, the strong base wins. The salt is basic. If I have the chaos scenario where I've got weak acid and weak base coming together, there's no way to do that just by looking without going to the numbers. I've got to look up the Ka and the Kb. And so depending upon what the relationship is, it could go any direction. But notice that whichever one is stronger is still going to dictate the acidity or the basicity of the salt. So let's look at an example of this. All I want to do here is predict the pH. Is it going to be acidic, basic, or neutral? And all I need to do is just split these salts down the middle, separate the cation and the anion from each other. If I do that, I end up with aluminum as a base would be aluminum hydroxide. Nitrate ion would come from nitric acid. So what I have here is a weak base, aluminum hydroxide, interacting with a strong acid, nitric acid. The acid is the stronger of the two. We would expect this to be an acidic salt. Since the salt is acidic, we know that that acidity comes from the cation. If push came to shove, and we actually needed to calculate the pH of this, we would look for the Ka value of the aluminum as our way to go about the calculation. Not there yet, but that's where we would look. Our second example, sodium is going to come from sodium hydroxide, NaOH. We know sodium hydroxide is a strong base. Carbonate ion is going to come from the hydrogen carbonate ion. We know that the hydrogen carbonate ion is a lousy acid. So the strong base wins, we would anticipate this to be a basic salt. Since it is a basic salt, we know that the basicity comes from the anion, and if push came to shove, we would need to do something with the Kb of the carbonate. Again, not there yet, but that's where we're headed. For the third example, we have calcium coming from the base, calcium hydroxide. And we've got chlorine coming from the acid, hydrochloric acid. Calcium hydroxide is one of our identified strong bases. Hydrochloric acid is identified as a strong acid. The acid strength and the base strength are considered to be equal to each other. So we would anticipate a neutral pH for calcium chloride. For our last example, we've got zinc iodate. Zinc would come from zinc hydroxide, which we know to be a weak base. Iodate would come from iodic acid, HiO3, which is not on any of our lists as a strong acid, so we would have to consider it weak as well. We've got a chaos situation. Weak interacting with weak. To remedy that, we would have to go to the Ka values, or the K values rather. So looking at the Ka of iodic acid versus the Kb of zinc hydroxide. Now, we already did an example earlier today with iodic acid. We know that iodic acid is a pretty good acid, 1.7 times 10 to the negative first. We probably know from experience that zinc hydroxide is not a great base, but we'll look it up anyway. 7.9 times 10 to the negative seventh. So we can see now that we've gone to the numbers, we can get rid of this question mark. The acid character is better than the base character. So we would anticipate this compound to be slightly acidic. Right. Any questions with qualitatively looking at pHs, or sorry, qualitatively guessing the acidity or basicity of a salt? Okay. So now we need to look at the quantitative side of it. And we're going to introduce this concept here because when we cover titrations in the next chapter, we're going to see this calculation come up again. And so we're kind of introducing it here to set things up for the future, knowing that we will see this again. But the idea here is taking that qualitative base and massaging it and using this conjugate relationship idea to figure out quantitatively what the actual pH of these solutions might be, at least from a theoretical standpoint. So we've already kind of talked about this concept when we were looking at the relationship between Ka, Kb, and water. Now we just have to put it into action. A bottle of chlorine bleach holds an aqueous solution that contains 82.5 grams per liter of sodium hypochlorite. What is the pH of this solution at 25 Celsius? So there are a couple of things that we need to take care of in this example in order to make some sense out of it. First thing that we're going to want to do is we want to look at what would we anticipate the characteristic of this salt to be. So if I look at, I've got sodium, so that means sodium hydroxide, which is a strong base. And I've got hypochlorite ion, which would have come from hypochlorous acid, which is a weak acid. I can see qualitatively that I expect this salt to be basic. And as a basic salt, we are going to rely on the anion to provide that basicity. So it's going to be the hypochlorite ion that does the work of acting like a base here. So that's the first thing that we do, is we can take that qualitative understanding, this should be basic, and we can turn that qualitative understanding into an equilibrium expression. Now we got to get into some of the other business. One, this concentration isn't a molarity, so we got to turn it into one. That's actually the easier of the two tasks. 82.5 grams of sodium hypochlorite in 1 liter of solution. Molar mass of sodium hypochlorite is 22.99 for the sodium, 16 for the oxygen, 35.45 for the chlorine. So 74.44 grams in 1 mole. So 82.5 divided by 74.44 would give a concentration of 1.11 molar. So if we're setting up our ice table here, we're starting with 1.11 molar hypochlorite ion. Water concentration we don't care about. Initial concentrations of the hypochlorous acid and the hydroxide are 0. So this sets up very much like most of our other ice tables have. And so, like I said, this is something that you kind of have to train yourself to recognize and to do. I've got a problem like this. I'm probably going to have to set up an ice table somewhere. The trick to this one was we had to set up the correct ice table. We had to know what it was that was reacting. But we're missing one thing, and it's an important thing. We may have the starting of an equilibrium expression here, but we don't have a K value. This is where we have to fall back on that idea of conjugate theory. You're not going to find in a table of references the Kb value of hypochlorite. But what you will find is that if you look, you will find a Ka value for its conjugate, hypochlorous acid. So if we go up, hypochlorous acid has a Ka value of 2.88 times 10 to the negative 8th. Remember, the relationship between Ka and Kb and Kw, Ka times Kb equals Kw. So my Kb value is equal to Kw over Ka. Kw is 1 times 10 to the negative 14th. Ka, we just found 2.88 times 10 to the negative 8th. So if I put that into the calculator, 3 sig figs, I get 3.47 times 10 to the negative 7th as my Kb value. So that is what I need to put in as the thing I'm trying to find in this equilibrium expression. Since my Kb value is relatively small, I can check and see if the 5% approximation would work here. 5% of 1.11 is 0.0555. So 5.5 times 10 to the negative 2nd. So we're talking about 5 orders of magnitude between that value and Kb. We can go ahead and ignore that negative x term. So that would give us 3.85 times 10 to the negative 7th is equal to x squared. .21 times 10 to the negative 4th molar for x. Which would also be our hydroxide concentration. So because of that, we can find the POH. Negative log of 6.21 times 10 to the negative fourth. Would give us 3.207. Remember your sig fig rules here. 3 sig figs means 3 decimal places in the POH. And pH is equal to 14 minus POH. So this would be set 10.793. So you probably knew already that chlorine bleach has basic tendencies. But now we have a good reason for why, both conceptually and assuming that the bottle has a similar concentration to this, mathematically, we can kind of put it into a frame. Any questions with this example? So just to kind of recap, you have to break it down into pieces. You look at the salt. You break the salt down into its acid and its base. From there, you look at it and say, oh, this one's a stronger acid than a base. It's going to be acidic. Or in this case, it's a stronger base than an acid. This is going to be basic. You take that basic tendency and you go, okay, basicity comes from anions. You show that anion acting as a base. Then you keep going. Since it's a base, you need a KB. You need to set up an ice table. You figure out the concentration of hydroxide. You turn that hydroxide concentration into a POH and then finally a pH. Now we've got one more question here. Just taking the temperature of the room, we're looking tired. So rather than have you do this one on your own and I go through it with you, why don't we try to work our way through it together? And you still put in your points and get your participation credit. So let's start with, we've got a 0.1 molar solution of sodium carbonate. What we need to figure out is, before we can get into anything else, what is this going to be? Is it going to be acidic or basic or neutral? And if it's neutral, well, that's easy. We just say it's about 7, we call it a day. So we got to break it into parts. What is the base that's giving us the sodium? Sodium hydroxide. What do we know about sodium hydroxide? What kind of base is it? Strong. Okay, let's look at the carbonate. What kind of acid is the carbonate coming from? right, this one's on the trickier side. The key is to add an H plus to the ion. So if I have the carbonate ion, which would be CO3 -2, I'm going to add a hydrogen to it. So the acid that gives us carbonate isn't carbonic acid, it's the bicarbonate ion. Remember, it's a polyprotic acid. Polyprotic acids lose stage-wise. So if I add together hydrogen with that ion and I don't come up with an acid, I've got to stop. I'm in the middle somewhere. Now, in other examples, it goes straight forward from there. It's okay, I can see this is chloride plus H plus is hydrochloric acid. I know that acid. Bicarbonate ion plus hydrogen is carbonic acid. I know that acid. That's easy. But for these ones where we've got a higher than -1 charge on them, the acid that they come from is going to be one of those amphiprotic in between ions. So I'm coming from the perspective of bicarbonate ion here. We know that bicarbonate ion, all of those amphiprotic ones are going to be weak. So right off the bat, we know that this is going to be a basic solution. Which part of the ion am I going to focus on from now on? What gives us our basicity? I can't hear you. No, there's no sodium hydroxide actually in this. We just use that as kind of a context to lead us to the fact that it's going to be basic. Because if it was sodium hydroxide, all I'd have to do is just, since I know it's a strong base, I know that the hydroxide concentration is 0.1, POH would be 1, pH would be 13. It's not that way though. If I know that I have a basic salt, I need to focus on that anion, the negatively charged substance. So I need to look at the carbonate here. So carbonate is going to act like a base toward water. Here's where we get to use that stuff that we talked about at the beginning of this chapter. If carbonate's acting as a base, and that means that water is acting as an acid. What are the two products? Yeah, HCO3 minus. So water is acting as a proton donor. It's going to give a hydrogen away to the carbonate. That's going to give us the bicarbonate. And after the water gives up that hydrogen, all that's going to be left is hydroxide. So we've done two things so far. We've correctly determined the approximate pH, basic, of this salt. And we've given ourselves the equilibrium expression that tells us it's going to be basic. Because we can see that one of the products of this reaction is going to be hydroxide ions. We've got two things left to do. three technically. We've got to set up our ice table. We've got to solve our equilibrium expression for the concentration of hydroxide so that we can figure out the POH and the POH and the pH. But before we can do that, we need to know the equilibrium constant for this expression. And that's where the bicarbonate is going to come in. We need to know the Ka value of the bicarbonate ion. So we got to go to our Ka value for bicarbonate is 4.7 times 10 to the negative 11th. Since our Ka value is 4.7 times 10 to the negative 11th, our Kb value is going to be 1 times 10 to the negative 14th over 4.7 times 10 to the negative 11th. Which would be 2.1 times 10 to the negative 4th. So now we have a value of K. We can set up our ice table. Don't need anything with water. We're starting with a 0.1 molar solution of carbonate ion, zeros for everything else, minus X for the carbonate, plus X for the bicarbonate and for the hydroxide. Okay, now this one's gonna be a little bit closer for the 5% approximation. 0.1 times 0.05 is 5 times 10 to the negative third. We're actually only about 1 order of magnitude away. I would advise actually leaving this one as it is. Whenever we get in that we're getting on the same order of magnitude or close to it within 1, it's better to do the quadratic and get because now we're going to get something that's a little bit non-zero if we don't estimate. So (2.1) times 10 to the negative 4th is going to be equal to X squared over 0.1 minus X we do a little bit of algebra here, we'll end up with 2.1 times 10 to the negative fifth minus 2.1 times 10 to the negative fourth x equals x squared. And so if we subtract x squared from both sides, so we're going to need some kind of equation solver for this. Our values are -1 for the x squared component, -2.1 times 10 to the negative fourth for the x component, and 2.1 times 10 to the negative fifth for the last component. We end up with an x value to two significant figures of 4.5 times 10 to the negative third and that is the concentration of the hydroxide. Now, if we had done the 5% approximation, 2.1 times 10 to the negative fifth, square root of that, we would have got 4.6 times 10 to the negative third. So not that different. And so if you had used the 5% approximation, you'd come up with roughly the same answer. You get marked, it wouldn't get marked wrong, but we're starting to kind of encroach on the area where the approximation is less effective. So that's what we need to be diligent about with that approximation. We don't want to overuse it and end up overestimating too much. So if you do the 5% and you see that you're within 1 order of magnitude of the value of K, then you back off, you think about maybe solving out the full quadratic. Certainly, if you get a value of K that's bigger than what you did with the 5%, you've got to do the quadratic then. But at any rate, the POH would be equal to the negative log of 4.5 times 10 to the negative third which would be 2.35. And that means the pH would be 11.65. All right, any questions with this last example? Yeah, Isha? We didn't do the carbonic acid because that's not where carbonate comes from. Remember, if we have polyprotic acids, they're going to lose their hydrogens step by step. So the conjugate base of carbonic acid is the bicarbonate ion. The conjugate base that carbonate's part of its conjugate acid is the bicarbonate ion. So we need to look at the bicarbonate ion as the acid that is acting here, not carbonic acid. We can only go up one conjugate step. We can't go up multiple conjugate steps. So when we're dealing with acids that have multiple steps to them, we can only go up or down one at a time. And so, yes, especially with acids, because acids tend to do this way more than bases do, it does get a little bit confusing there when we're looking at acid behavior. But that's why we only went up the one station instead of the two. All right, any other questions? All right, one last thing then. Your last confidence meter of chapter 15. I have a feeling I know what this one's going to tell me, but I need you to say it anyway.